Hello everyone. Today let's continue to talk about the modular logic circuit. Today's topic is three-state buffer and magnitude comparator. A buffer is a special logic device that the output follows the input signal. So the main application for buffer is to increase the drive capability of a gate output. If we look at the graph on the right, think we have a AND gate, and we want to collect its output to another gate. If there's only one OR gate, that's okay, because all the output current from the AND gate will go into the OR gate. Okay, so it won't cause big delays. However, if we want to send the output signal of this OR gate to multiple AND gates that's in parallel, which means we have to split the output current into different parts and send it to each of the AND gate here. And that will cause big delay, time delay. Okay, and sometimes it's intolerable. To solve this issue, people usually insert a buffer between those two levels of gates. You can think the buffer still keeps the logic value of the input, but it will increase the current level, so it has enough current to distribute it to different gates there. Then the total delay is still maintained in an acceptable level. Okay, so that's the main application for buffers. But today, the buffer we are talking about is a special buffer. It's called tri-state buffer. From the name tri-state, you probably can figure out that this buffer has three outputs. Before this slide, everything we talk about has only two values, right? We're talking about only Boolean values, 0 or 1s. But in this special buffer, it has a third state. It's called high impedance state, and we use letter Z to represent it. Okay, Z is neither 0 nor 1. It's just showing a high resistance at the output, like no signal come out. Okay. So here is a symbol for the tri-state buffer. For regular buffer, you have one input and one output. A very similar device is inverter, if you remember. Okay, but in this device we have an extra input, which is a control input, B. So you can think B as a switch. If normally, in most cases, if B is 0, you can think this switch is in open state, like the input signal cannot go to the output C here. So this C will equal to the high impedance state, Z. Okay. When B equal to 1, this switch is closed here. So now the output C will follow the input values. So that's the basic operation for tri-state buffer. But depending on the active level of the control input and the output, we have 4 versions of the tri-state buffer. So the first is the normal version. So B is active high. So this 1 will turn on this buffer, right? So when B equal to 1, the C will follow A. But if B equal to 0, it doesn't matter what input you have, the output always Z, always equal to Z, high impedance. However, if we add a bubble at the output here, so if you remember, if you look this looks very similar to a NOT gate, right? So in this case, when B equal to 1, then the output will be the opposite of input. But when B equal to 0, the output is still Z. Also, we can design a buffer that has opposite active level for the control input. So in this case, when B is 0, the switch is closed. Then the output follow input. But when B is 1, the output is in Z state. The last one, you can think this is as the inverter with active no control input B here. Right? When B is 0, output is the opposite or complement of the input. When B is 1, the output is in Z state. One useful application for the tri-state buffer is to use them as the multiplexer. So if you check this logic diagram as shown here, so we can use two such buffers to realize the function of mux. In this case, if the control input b equal to 0, actually the top buffer will be on, right? So D will follow A. If B equal to 1, then the bottom buffer will be on, and D will follow C. That's the function for 2-to-1 multiplexer. And if we use 3 of such structure, we can realize a 4-to-1 mux, as shown here. So we have one such pair here, one such pair here, and the third pair here, right? So let's do a quick analysis. So if they select the input S1, S0 equal to 0, 0, so this is 0. 0 means the top buffer will be on. So Y1 will follow D0, Y2 will follow D2. But in the second level, S1 equal to 0, so only Y1 will pass through. So the output Y actually equal to Y1 equal to D0. If S1, S0 equal to 0, 1, so now this is 1 now. 1 means the bottom buffer will be on. So Y1 will equal to D1 in this case. Y2 equal to D3 in this case. But S1 is still 0, so only Y1 is passed through. So Y1 equal to D1 here. For 1, 0, this is 0, so still Y1 equal to D0. Y2 will equal to D2. And Y, because S1 is 1 now, so Y will follow Y2. So Y2 is D2 in this case. Finally, 1, 1. So this is 1. You will find Y1 equal to D1, Y2 equal to D3. And S1 is 1 here. So Y2 will pass through, which equal to D3. So if you check this output column, you will see this exactly the function of 4-to-1 mux. And you can think about how to use this to make like 8-to-1 or even 16-to-1 mux. It's very simple. Another useful application for tri-state buffer is that we can use it to help build the bidirectional pin. Like this is a pin allow data to flow out, but also in some cases we can use it as the input pin, okay? or sometimes what we call in and output pin, input and output pin. Okay, so bidirectional flow of the data. How is realized in this logic diagram? We can see that we have a 3-state buffer here. Say the enable input or the control input equal to 0. We will find Y will be what? 0 is not active state, so Y will be the high impedance states, right? Which means the data cannot go out, but we can send the signal here to let the data flow into the internal circuit. So when enable equal to 0, this pin will be used as the input pin. When enable equal to 1, now we can't put signal here. Actually, the signal will come from the output of this circuit. So this Y will equal to the output of this circuit. So this is used as output pin. Okay, the last modular circuit we want to talk about is a magnitude comparator. A comparator is an arithmetic device that determines the relative magnitude of two binary numbers. So basically, we just compare two numbers, tell which one is bigger or they are equal. All right. So say we have two n-bit binary number here, and when we compare them, there are only three possible outputs, right? Either A is less than B, so we write ALTB, or A equal to B, A equal to B, A equal to B, or A is greater than B. Right? There's no other option, just those three results. But how to realize this using logic circuit? Again, let's start with the simplest case. Say we have A and B. We only think about 1-bit binary number here. So two numbers, each number has only 1 bit. And we still have three results, right? A less than B, A equal to B, and A greater than B. So if we write down all the possible combination for those two numbers, so 0, 0, we know A equal to B, right? So this will be active. Now we just assume it's active high. You can also design circuit with active no, with no issue. So 0, 0, 0, 1, B is greater, so A is less than B. 1, 0, A is greater than B. And finally, 1, 1, A equal to B. So for this 1 bit, we can simply draw a circuit like that. Because A equal to B is an X NOR function. Right? If we compare the truth table with X NOR gate, this X NOR function. And for A less than B and A greater than B, it's just an add function. Only one output is 1. That's an add function. Okay, but what I want to point out here is that we actually have a different way to represent A greater than B or A less than B. But let's do this. So think about this. Because we talk about there are only three possible answers, right? When we compare two numbers. So A greater than B basically means A not equal to B. And at the same time, A is not less than B, right? So basically, A greater than B should equal to this too. So we have an alternative way to do this. So for A greater than B, we don't have to do that. What we can do is take the output of A equal to B, put it goes through a NOT gate, and find the output of A less than B, and put it through a NOT gate, then put them go through an AND gate. We still get A greater than B. Okay, so this is a different way to represent this. And why I mention that is that even though right now for 1 bit the A greater than B, using this circuit still simple, but when we have multiple bits comparator, things getting complicated. But this relation still is valid all the time. So if we do this for multiple bits comparator, it's much easier, right? You can tell we only have 2 NOT gate and 1 AND gate. That's all. Okay, let's find out this using 2-bit comparator. Again, so let's figure out the truth table first, because that's always the standard way to design a logic circuit. So we are comparing 2-bit binaries. Then there are like total 16 different combinations. Right? So 0, 0, 0, we know it's 0, 1, 0. They are equal. 0, 0, 0, 1. So A will be less than B. 0, 0, 1, 0. A less than B. A less than B. Now A greater than B. A the 5, I think, yeah, that's a mistake here. So 0, 1, 0, 1, that's A equal to B. 1, 1, 0, A less than B. 0, 1, 1, 1, A less than B. 1, 0, 0, A greater than B. 1, 0, 0, 1, greater than B. Now equal, less than, greater, 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 equal. Okay, so you can solve this truth table using column map, right, to figure out the simplest Boolean expression and do the circuit. That's a normal way. But we can also do this using a more clever, more simplified way. So we think about this. In the previous slides, we talked about when A equal to B for 1 bit. Actually, that's XNOR function, right? So now for 2 bits, we still think about when they are equal. So basically, it happens when both of those 2 bits are equal individually, right? So A1 equal to B1 and the lower bit A0 equal to B0. So for this, we can directly write when A equal to B, when A1 equal to B1, then it can be written as A1 XNOR B1, and at the same time A0 XNOR B0. Basically, X1 XNOR B1 means A1 equal to B1. This means A0 equal to B0. So if both of them happen together, we say A equal to B. Then when A is greater than B, 2 cases. If the higher bit A1 is larger than B1, then we don't have to compare the lower bit, and we know A1 is greater than B1, right? Another case is if A1 equal to B1, then we have to compare the lower bit, and we say A greater than B if A0 larger than B0. Also, just like A equal to B, we can directly write this: A greater than B should equal to either A1 B1 not is true, right? So A equal to 1, B equal to 0, which means A1 bigger than B1, right? Or A1 equal to B1, but A0 is larger than B0. So this is corresponding to the second case. So that's a function. You can do similar for A less than B. When this would happen, when A1 is 0, B1 is 1, right? Or if A1 equal to B1, and at the same time A0 is smaller than B0, then we say A is less than B. Or like what I said before, it's still equal to A not equal to B, and A not greater than B. This is still valid. So if you draw this out, you get this diagram here. Okay. Use similar idea, we can directly write out the Boolean expression for the 4-bit comparator. Right? You can understand it this way. A equal to B happens when all the 4 bits are equal. Right? A greater than B equal either A3 larger than B3, or if A3, B3 equal to each other, then we compare A2 and B2. If both the higher 2 bits are equal, we compare the third bit, A1 and B1. Finally, if all the three bits are equal, we compare the LSB to C, right? And for the other output, just do this, not equal and not greater than. Very simple, right? You can keep doing this for 8-bit, 16-bit, but for the 4-bit, we have some standard modules. So if we fabricate those logic gates in a single microchip, we get this module, comparator 4-bit comparator module, and this module can be cascaded to 8-bit or 12-bit, 16-bit, as many as you want. Okay, so that's all I want to talk about concerning modular circuit. And starting from next lecture, we will start talking about sequential logic circuit. Okay, if you like my video, please help share and subscribe. I will see you next time.